So now we're going to dig into that. Was Bohr model was okay for a while, and there's Kristen. The Bohr model was good for a while, and it still has its applications, but a more complete understanding of the atomic structure, especially how the electrons are positioned in that space around the nucleus, requires a better theory. And we're going to start with this idea, which was proposed by Heisenberg. Let's see, is that a U or E? I never can. E. It's called the uncertainty principle. Now, I believe Heisenberg came up with the uncertainty principle in general mathematical terms, but for applications to things as small as atoms and subatomic particles, it's extremely useful. And it simply says that the uncertainty in knowledge of where something is, and we designate that with a delta x, x meaning position. Right? So the uncertainty can be this big or even smaller, times the uncertainty in momentum. Mass times velocity is momentum. And if you're talking about just the electrons, right, the mass is going to be the same anyway. So we're really talking about how fast is it going, or what is its energy, right? If we apply mass and velocity to a calculation of kinetic energy, then we can say something about the energy of that particle. Well, the degree of uncertainty here times the degree of uncertainty there will always be greater than or equal to this number. Of course, 4 pi is a constant. H is Planck's constant. Right? That really looks like a big number until you get to the negative power of 10. So what that means is, and since these are all constants, then that's a constant value. So what's happening here is if this one goes up, that one goes down. It's the typical inverse relationship. So our uncertainty in knowledge of where something is, if that uncertainty goes up, then the uncertainty of its velocity or energy goes down. And we can get closer to what the true value is. If we let this one go up and we don't really care where it is, then we can gain some more precise information about what its energy is. And vice versa. If we want to fix where something is, then we really can't say anything about how fast it's going or what its energy is. So it's a trade-off. Now, and this was essential knowledge to making this particular theory work because the particles are so small. There were a host of other scientists that have contributed over the years to the quantum mechanical model of the atom. And I just named a few down there. We might look at de Broglie eventually. De Broglie was just, I mean, he was so brilliant, he was kind of weird. You know how that goes. Schrodinger came up with the wave equations that describe the nature of the electron in its various positions around the atom. Max Born, Dirac, Paul Dirac was kind of weird too. He was one of those mathematical geniuses. Pauli was more down to earth. Einstein was just as earthbound as you can get. But there were many others. Okay, so if we go to Schrodinger's equations, one of the terms that we find in the equations, and we're not going to try to solve any problems with equations. We're just using them to help us understand whatever we can in our limited sphere of what's happening with these electrons based upon the wave equation. And remember, if light has both wave and particle nature, like we discussed last week, particles can have particle and wave nature also. And de Broglie addressed that problem, and we'll hopefully talk about that one later, or even when we get to discussing solutions to our review document problems. But there was a term in Schrodinger's equations called the psi function. And it was, I think it was squared. What this indicates in the equation itself is a probability of finding an electron at or near a particular point in space. So if this value increases, then our probability of finding the particle right there increases. So as we do that, once we can identify where we think it is, then that decreases the accuracy of our energy term, right? Because of Heisenberg's uncertainty. So there's a trade-off there. So what we end up doing is, since energy is a more important term to understand about electrons than their position, then we let the position turn into this probability function. And we just say, the electrons are probably in this space, somewhere in this space. And that's close enough for chemistry. It's more important that we know what is their energy. So when we take the wave function for an electron, a hydrogen electron, and that 1s won't mean anything yet. I haven't described what that means. But this one electron that's surrounding it's out here somewhere. With the hydrogen atom, this probability distribution says, all right, the wave function tells us that this electron is going to be more than likely in this region, very high probability right there. And then as we move away, the probability is going to decrease. That's what that graph is trying to show, except for one flaw. The probability of finding an electron right at the proton is 0. Right? So it really should go something like this. It should start here, go way up here like that, and then tail off. Okay. So that's what the psi function is trying to tell us. Give us a probability of finding an electron in a particular space. That's a better one. There you go. Okay. So the orbital size is difficult to represent simply because of this uncertainty in position. So we use that psi function to tell us, well, it's probably here, but it could be over here. It's more than likely here. So that if the probability goes up, we're saying this is kind of a central point, and on either side of that, the probability drops off. We're pretty sure it's in this area. And remember that when we draw these graphs like that, those are two-dimensional representations. Atoms are three-dimensional. Right? So these wave functions have to describe their distribution in three-dimensional space, which is a little difficult to do on a flat surface. This probability expression for the hydrogen atom, and we're going to start off simple, right? With the hydrogen atom, the what we propose as the radius of this sphere for the size of the atom is an idea that encompasses 90% of the probability of finding it there. And then outside that sphere, it drops off rapidly for the other 10%. But it doesn't completely exclude finding an electron in that space. Okay, now I'm going to get to everybody's favorite discussion numbers. And these wave equations that Schrodinger proposed had 4 numbers that were associated with them. And if you plug these numbers in, the equations would spit out values that told you this is where we're likely to find that electron, and this is the energy that it will have. So these quantum numbers are related to Schrodinger's equation. Right? The first one derives from the Bohr model, the principal quantum number. Right? And the principal quantum number is given n, and it starts at 1 and goes in whole number increments up in increasing energy. Right? That's the easiest one. And it generally describes not only the energy of the that is encompassed by that region of space, but the size also. So as you get bigger in the numbers, you get higher in energy, and the probability of finding the electron moves further away from the nucleus, which is an expression of increased energy. The increased energy is derived from the idea that if you have an electron down here and you add energy to it, it's going to jump to a higher orbital, right? So that's a higher energy. So 1 would be here, 2 here, 3. So that's what we're getting at with these numbers. So we're expressing, let's see, we're expressing size and energy with that number. The next number, the angular momentum. I don't know what, azimuthal, it just doesn't flow off the tongue. Angular momentum. So the angular momentum quantum number is given the letter L, and it's derived from any one of these. So it's kind of like a branching tree. If you could take this one or this one or this one, and each one of those would have a set of L's assigned to it. Okay, that's an important concept here. So you take your n number and you start at 0, and then you go up in whole number increments until you get to n minus 1. So the L can't be any higher than 3 for this one, or 2 for that one, or 1 for that one. Okay. So, for instance, if we went up to 4, then we could possibly have a series of L numbers that were 0, 1, 2, and 3. They would be available. Okay. And what we're talking about here is the shape of the orbital. Okay. This is often referred to as a shell, the end, and this is often referred to as a subshell. Okay, I'll leave that there for now. Hopefully it'll make more sense once we try to build an atom with its electrons. The next one is the magnetic quantum number. And it's given the letter M sub L. Okay, and it derives from any one of these L's. So if you take an L of any size, you would start at negative L, and you would go up by whole number increments to 0, and then to positive L. So if we went back to say we had this level 4, and then we took the L from that one, say 3 is 1, 2, and 3. We would take 3 from this level, we go 4 here and 3 here. Then the possibilities here would be -3, -2, -1, 0, +1, +2, and +3. Those would be the possible M sub L's for an L equal to 3. Okay. And the magnetic quantum number is referring to orientation in three-dimensional space. Which way is it pointing? And then the last one's actually the easiest one. The electron spin. And this can either be +1/2 or -1/2. That's the only two choices. So any one of these L numbers can have either a +1/2 or -1/2. Okay. And that's just what it says. It refers to the spin of the electron. Is it going this way or is it going that way? Okay. Now, I'm not sure how much help this table would be. It just shows that if you start at n equals 1, then the only possibility for L is 0 because it's 1 minus 1 is 0. That's it. So at this level, 0 is it. And then if you only have 0 here, then you can only have 1 there, right? Because go from -0 to +0. And then, but you can't have a +1/2 and a -1/2 for that one. So that's why there's only one orbital. And that's what this level is referred to as an orbital. Okay. So if you have an n equals 2, the only possibilities here is 0 and 1. Right? You can't have a 2 L level. To simplify things, when we start to define what the electronic structure of an atom is, we give these letters. So we use the numbers here, and then we use letters to represent these. Let me go up to 3 here. So if it's L is 0, that's an S subshell. 1 is a P subshell. 2 is a D subshell, and 3 is an F subshell. And that's as many as you need to get all of the elements in the periodic table covered. So when we say 1s, that could be hydrogen, but it could be any other element because we're building from the lowest up. So every element in the periodic table has a 1s subshell. Okay, we're building from the inside out. All right, for principal quantum level n equals 3, right? If we go to that one, determine the number of allowed subshells. So how many of these are allowed? Right? Well, 0, 1, and 2, because 2 is n minus 1. So you can only have 3 subshells at n equals 3. Okay. And the different values, of course, are 0, 1, and 2 are S, P, and D. Okay. So we would say for that particular subshell, it would either be a 3S or a 3P or a 3D. designation for the subshells. Those are the possibilities. Now, we may not use them. Only if you have electrons to go into those subshells are you actually going to use them. But they're there, just waiting for something to go into place. Okay, let's try another one. Take this one back to there. For L equals 2. L equals 2, okay? We've come down to 2. Now 2 could be found in n equals 3 or 4 or above. Can't be found here because 2 minus 1 is the highest you can go, and that's 1. So if your n equals 2, can't go any higher than 1. What's the magnetic quantum number? Magnetic quantum numbers and the number of orbitals. So the magnetic quantum number would be at 2, would be -2, -1, 0, +1, +2. So you could have 5 orbitals at that subshell. The D subshell can have 5 orbitals. Okay. Okay, so let's look at the shapes and energies. Shapes and energies in terms of 1s, 2s, and 3s orbitals. So if we have 1s and then we have a 2s or we have a 3s, how do they compare with one another? Right, the 1s starts with a high probability, and I assume that there's a 0 space. I mean, you can't be right at the nucleus. That's impossible. But the probability of finding one goes down. And the 1s orbital has a 90% probability density equivalent to the far left-hand blue sphere. That one or the one below it is another representation. Since this represents size also, then the 2 is going to be bigger. But the 2 also has a place in there where the probability of finding the electron goes to 0. That's called a node. So for the 2s, we have a bigger shape and higher energy probability, but we also have a node in there where the equation says you're not going to find an electron there. Similarly, if you go up to a 3s, we're going to have 2 nodes where you won't find an electron, but the size is much bigger and the energy level is much bigger. All right. When we get to the P subshells, notice that when we have the S subshell, then the orientation is spherical, right? It's equal in all directions. But when we get to the P orbitals, you can have a -1, 0, or a +1. So a -1 at P equals m sub L would give you a different orientation. And this is the easiest one for me to understand, because on a 3-dimensional scale, you can have an X, Y, or Z axis. Well, if you have P1 here, then that's possible -1, 0, and +1. And this would be X, Y, or Z orientation. So we could say -1 would be that X orientation, 0 would be the Y orientation, and +1 would be the Z orientation. Because that's what it's talking about right here. Now, when we go up to the D's, things start to get really hairy. Right? You're not on an axis. You're kind of splitting axes. And then the last one, you get a donut. So we're not gonna dig into these too deep, and especially not if we go to F orbitals. Right? They get really wild. And these are not observed shapes. We don't see this. This is probability calculations from the equations. This is what we would expect to see if we were small enough and our observation didn't interfere with things. And that's another concept altogether. When you observe something that small, the act of observing changes it, right? So we're not going to go there. That's a little too deep for this course. Okay, then we come to electron spin. And once you get down, once you drill down from here, say one of these to one of these to one of these, then within whatever we decide is the combination of this one, this one, this one, you can have either a +1/2 or a -1/2. So that means once you get down to the orbital level, you can put 2 electrons in that orbital. Right? +1/2, -1/2. Maximum. You don't have to, but you can. And this brings us to the Pauli exclusion principle. Pauli said that in any given atom, no 2 electrons can have the exact same combination of 4 quantum numbers. They're all a unique set. If you have the same number here and the same number here and the same number here, then you'd have a +1/2 and a -1/2 designated for that for this electron versus that electron. That's just so we don't try to say the 2 electrons have exactly the same quantum characteristics. They can't. Each electron is unique in terms of its quantum wave function. So up to now, we've been focused on the hydrogen atom. And the reason for that is there's only 1 electron, or ions that only have 1 electron. But as a matter of fact, there's only 1 element in the periodic table that only has 1 electron. And the rest of them, for neutral atoms, they have more than 1 electron. Those are polyelectronics. Since we don't know how the electrons are moving, and we know that they are negatively charged, so they're going to repel one another, then we can't calculate exactly what that repulsive force is or what it does to their paths. Right? So we treat electrons differently than we would, say, a baseball or a bowling ball, right? As a particle only. We treat electrons as waves. That's where Schrodinger was going with his equation set. But we do, when we're building electrons, we build them from the lowest energy out. So the lowest energy would be the hydrogen electron. And the hydrogen with 1 proton and 1 electron would simply be 1s with 1 electron in it. That's the way we write it, right? It's quantum, principal quantum 1, angular momentum S or 0, and then we have 1 electron in that one. And then for the next one, say if we wanted to draw helium, it has 2 electrons. So we always go from the lowest energy, and we don't move to the next highest energy until these are filled. Right? That's got a name. It's called the, where is it? I thought I had the rules in here. Huh. That's the Aufbau principle. Aufbau is a German word. I don't speak German. I just have to take somebody's word for it. As I understand it, Aufbau means do it this way. So it just means you fill things from low energy to high energy. Okay, next. So here's the effect that polyelectronics has on the energy levels. What we find is that 1s, of course, is down here by itself. Once you get to the n equals 2, then what that does to the subshells is it tends to increase the energy slightly in the L equals 1 for the p orbitals. They're just slightly higher. And then the same thing for the 3s. You get the s's, and the 3p's are a little higher, and the d's are a little higher. So what that says to me is that there's not a whole lot of difference between them, but it is significant. And when we say this designates their energy level, it's really an energy region. Now, what this does, as you put electrons into those levels, let's see, and we'll get to that in a minute. As you put electrons into those levels, it accentuates that difference in energy even more because of the repulsive effect, right? These electrons in the Ds are close in size and in position, and they're pushing against each other. So the ones that lose, that have to go to the higher energy level, are the higher energy orbitals. They get pushed away. So we see as we get more electrons in there, it tends to spread those out, that energy difference even more. And you can get to the point where a third level energy might actually be higher than a fourth level energy. We're going to see that in just a minute. But first, I want to talk about this concept called the penetration effect. And we've got some graphs to help you understand that. If you peeked ahead, you've probably seen them. The 2s electron penetrates to the nucleus more than the 2p. So what do we mean by that? Well, if we draw, remember when we drew the distance here between and the energies, right? So this is distance, this is energy. If we talk about the 1s, it's going to be like this. We talk about the 2s, it's going to be more like this. Let's see, that's too high. 2s. Actually, yeah, that's right. 2s is going to be more like this and like that. Right, so most of its probability is out here at higher energies. And so we can see that. Well, when we say penetration, the probability, we're talking in terms of probability. The probability of finding electrons, there's a slight probability of finding some down here, you know, close to the 1s orbital. But most of them are out here. So that gives us an averaging effect of putting the 2s at a higher energy level. When we talk about 2p's, then the 2p actually has an energy level that goes in like this. Let's see. I think it's like that. And then out here like that. So this one would be 2p. 2p. The penetration effect of the 2s means that even though 2p has a hump down here, the 2s actually penetrates closer to the nucleus than the 2p. That's what we're trying to say. And that gives the overall effect of a lower energy for the 2s in probability terms than the 2p. Let's see, I think I got it. Here we go. This is better. All right, so I didn't draw it just exactly right. What this is trying to show you there, the 2p is in that orange line and the 2s is in the red line. The highest probability for the 2s is at a greater distance than the 2p. But the 2s also has a probability below the 2p. That's the penetration effect. It penetrates closer to the nucleus than the 2p does. Does that make any sense? Right now it does. Maybe an hour from now, try to remember what I said and see if it works. So the 3s, since it has two nodes, has probabilities that are closer to the nucleus. This is the penetration effect for the 2s orbital. So if we compare the s's, we find that the 3s has a penetration very close to the nucleus that's even higher than the 3p. And the 3d, of course, has a lower energy, a majority lower energy than the p or the s, but it has no penetration toward the nucleus. So what that tells me is that we get this shift in energy that we saw on that former graph, but overall, we have to defer to the penetration of the S and the P being closer to the nucleus than the D. All right, let's talk about the periodic table. I think it'll, take the pressure off for a moment. This is a little too much math. All right, the periodic table, as we see it now, it didn't come that way. It took many decades to get it to this form. The first attempt to recognize some sort of relationship among the elements was by Johann Dobereiner. And he came up with this concept called the triads. He noticed that these elements here, right, chlorine, bromine, iodine, had similar chemical reactivity with other elements. They weren't exactly the same, but they were fairly similar. So he called that one of his triads. He's had several others that he identified as triads, but he didn't go much further with it than that. Okay, then along came two scientists that were working approximately the same time. Julius Lothar Meyer was German, and Dmitry Mendeleev was a Russian. And they also saw these relationships. And Meyer presented his in sort of a table form, but it wasn't organized like this. Mendeleev worked based on the principles of Dobereiner. Mendeleev said, okay, there seem to be a lot of elements that have similar characteristics, right? Not just triads, but there were whole lists of elements that had similar characteristics. And he went further than that. He said, this is their relationship in terms of physical properties like boiling point, melting point, chemical reactivity, whatever that happens to be, and some other things. And he was very meticulous in describing how they behaved and how they were related to one another. And he presented his periodic table. His first one was, he had what we call the groups. We used to call them families. Elements like the halogens would be a group. He had them horizontally. Right? That was his first publication. The second publication, he rotated them 90 degrees. And more importantly, he was using what he knew about this periodicity, and I'll describe that in just a second, to position elements in their proper groups. And he noticed that of all the elements that we knew, if you went by weights, and in those days, that was what they knew. They had a system of atomic weights. They weren't particularly accurate, but they did progress as the element got heavier. They could arrange them by atomic weights. So he arranged elements and atomic weights, and he'd come to a spot where he'd have groups. We'd have elements here like that. And then this place right here, there's an element that came next. And he said, wait a minute, It's nothing like these elements. It's more like this group over here. So he just moved it over one group and left this one blank. But he didn't just leave it blank. He said one day there will be an element discovered that will fit this position. And it'll have these properties. Bang, 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 bang. And they found every one of them that he predicted, they found them. And they had similar properties that he predicted. That's why Mendeleev has his name more closely associated with the periodic table than any other scientist. Now, what do we mean by the periodic nature or periodic, the periodic table? Well, it is a table, right? It has rows and columns. The columns, of course, right? Like this, over here, like this, like that, right? The columns, and then we should have 6 over here. Let's see. Like that. The columns were the elements that had similar nature. Well, when we think about periodicity, does anybody know what periodic motion means? Think of grandfather clock, the pendulum. That's a periodic motion, because a periodic motion does move, right? That pendulum moves, but it goes out here and it comes back to this where it was. That's one period. And it goes through here. It's back to the same place. So when we're adding elements and we go from, now we go from atomic number, we increase from left to right. Once we get out here and we go to the next one, say the next heaviest one is out here, but it has characteristics like this one over here. So instead of adding another column, we just say we're starting a new period. Okay? So we go over here, start a new period with that element. We've gone through one period cycle in the periodic table. That's what we mean by period in the periodic table. All right. Now, this is what it looks like. And the construction here is purposeful. In other words, if you know how the periodic table is built like this, then it's easier to construct its electronic configuration. And I'll show you what that means in just a minute. Let's see. You guys, did any of you do the periodic table exercise? The extra credit? Yeah, okay. So you learned that some of these groups have names. Alkali metals are the first group, alkaline earths the second group, transition elements across the bottom. And then we get to the first 2 here, and the last 6 are called representative elements. I don't know where that name came from. But when you go to the far right, of course, you get the noble gases. And then to the left one, you get the halogens. And to the left again, you get the chalcogens, the oxygen group. And then to the left of those, the nitrogen group, which is the pnictogens. Starts with a P, but the P's silent. And then you get the carbon and the boron group. They don't have special names. Then you get these 2 groups down here at the bottom, the lanthanides and the actinides. The lanthanides, we pull them out of the periodic table where lanthanum starts and actinium starts. So these would be plugged into that space between lanthanum and hafnium. And we do it for 2 reasons. One is we don't want our table to be this long, this wide. And the other is how the electrons go into those orbitals. Right? I'll describe that in just a minute. Okay. The modern way to identify columns is just sequence from left to right, 1 through 18. But the older sequence, the way I learned it, was the Roman numeral 1, 2, 3, 4, 5, 6, 7, 8. What that allows you to do is to instantly know how many electrons are in the outermost shell. because those are the ones that react. Right? We have core electrons, and then we have what we call valence electrons. Those in the outermost shell, those are the ones that are responsible for chemical reaction. The core electrons are just there for other purposes. And the representative elements, these two groups, they behave more predictably than these guys in here, the transitions. Okay, the table is divided into roughly two regions, right? Non-metals on the right, metals on the left, including the lanthanides and actinides. So most of the elements in the periodic table are metals. And they share characteristics. There's a zigzag line. On this table it's in red, but when you did the extra credit, I asked you to do it in black, just so it stand out more. But you start between boron and aluminum, and then you stair step like that. And that's it. These are non-metals, these are metals. Those blue ones, and it varies which ones are identified in those blues. Some of them, some authors don't identify them, but they're called metalloids. And the reason they're called metalloids, oid means similar to, like android, like robots, androids, they're similar to humans. Metalloids are similar to metals. If they're non-metals, sometimes they behave like metals and sometimes they behave like non-metals. Similar for on the other side of that line. These might behave like metals sometimes and non-metals like others. It depends on the reaction environment. What are they reacting with? There's the Aufbau principle. I need to shift those slides around. I think it makes more sense the way I tried to present it. So this Aufbau principle just says that you fill the orbitals from lowest energy to highest energy. And an example there is oxygen. So if we start off with oxygen, and we're gonna start off with neutral atoms. So if we have oxygen says 8 protons, that means we have 8 electrons. Right? So the n equals 1 can only have one L value at the S. That's it, because that's n minus 1 is 0. That's as far as you can go. And you can have only one of these, M sub L's, and then 2 electrons each. Okay? The next, you can go up to 2. Okay? 2 can have an s orbital, and it can also have a p orbital, because with 2, you can have 0 and 1. Okay? So let's see. If we're going to fill the electrons in here, s orbitals can have 2 electrons. Okay? So we can use up 2 of them. Use up 2 more. That's 4. So we got 4 electrons left. So far, so good. Okay. We got 4 electrons left that can go in here. How many can the 2 p's hold? Well, if we get to p, what do we have available? We have -1, 0, and +1, right? And 2 for each. So we can have 6 electrons in the p, right? If we get to p, you can have m sub l's, -1, 0, +1. And each one of those can have left and right spin, plus and minus. So that's 6 total. Well, we only have 4, so we can put them all right there. That's as far as we go. Now we have built the oxygen. Now, if we go down to finer detail, right, where we actually take these values, -1, 0, and +1, then there would be 3 orbitals in this subshell, right? -1, 0, +1, or X, Y, and Z. And then we could put them in there. Let's see, I need another rule to go by. Hund's rule. If that's the case, Hund said that when you start putting them into these orbitals from a given subshell, you have to put them in unpaired first, like spin up, +1/2. The next one spin up, next one spin up. So we've put them in as far as we can go, right? And we got one more electron left. If you have electrons left over after you put in separate orbital electrons, then you can start pairing them up. So now we can put the spin down in this one. Okay? Takes practice. That's Hund's rule. So your authors like the double barbed arrows. I don't. It's too much trouble. But that's what oxygen looks like, right? You'll have these two electrons are paired. These two are unpaired. Now that's significant when we start to try to explain behaviors, right? We'll get to that in a minute. In fact, this model explains behaviors that previous models cannot. And that's one of the tests that we use to confirm the validity of a given theory and the model that goes with it. All right, I mentioned valence electrons. So by definition, valence electrons go to the highest numbered orbitals. So this one, 2 and 2, that's the highest N number. Okay, so it has how many valence electrons? 1, 2, 6. So oxygen has 6 valence electrons. Okay. Have you heard of the octet rule? Sometimes you get it in biology and anatomy and physiology if the instructor wants to teach a little bit of chemistry. Otherwise, you've never heard of it. The octet rule simply says for some elements, particularly those in period 1, 2 and 3, 2 and 3, a complete highest level orbital, in this case 2, is going to be 8 electrons. Right? If we fill this up, we put 2 more there, that's 6 and 2 is 8. That's the octet. And when you do that, then you look like, for oxygen, you look like neon. Because now you have 10 electrons, right? 2, 4, and 6 is 10. The reason the octet rule is useful is that it partially explains why one element reacts with another element the way it does. Because they're all trying to fill these orbitals. They're trying to look like noble gases because that's the most stable electronic configuration that we know. So when oxygen reacts with hydrogens, right, it reacts with 2 hydrogens, right? So 2 of these would be a 1s1 and another one would be a 1s1. So this hydrogen shares this electron over here, bumping it up to 5. This one shares another electron, bumping it up to 6. Now we got an octet. Oxygen's happy. Hydrogen's happy because it shared one of these electrons with itself. And hydrogen only needs a duet because it only has the 1s orbital. So 2 electrons, it's perfect. Then it looks like helium. Okay? All right. So now we come to the periodic table and how it's structured. What are the highest orbitals that are being filled? Those valence orbitals. The highest orbitals, actually not orbitals, but subshells. What are the highest subshells that are being filled? Well, if you're in the first and second column, those are the s orbitals that are being filled. Right? So when you get to s, there's only room for 2 electrons, right? 2 electrons. Alkaline metals, alkaline earths. When you get to this side, you're filling p orbitals. Right? How many electrons can go in p orbitals? Well, we've got -1, 0, and +1 times 2 is 6. So you have 6 electrons available. How many columns do you have? 6. So 6 electrons are operating in this region where you have 6 columns. Okay? When you get to the transition elements, you're filling d orbitals. And d orbitals are 2, which means you can have -2, -1, 0, +1, +2. That's 5. You have 5 possible orbitals for the d's. 2 times 5 is 10. So you have the possibility in any given period for 10 elements across there. And count them from scandium to zinc is 10 elements. Okay? How about F, right? The 3s. -3, -2, -1, 0, +1, +2, +3. That's 7. Times 2 is 14. So you have room for 14 elements. And you count across the actinides, there are 14 elements. So with that knowledge and understanding which orbitals are being filled with any succession of elements in a period, you can build the electronic structure without having to go back to the rules that govern the building of the atom, building of the electron structure. We're going to do that as an example in just a minute, but I don't waste too much time talking. This is useful sometimes. What this does is takes into account the differences in energy levels with polyelectronic elements. And what you see is down the left-hand side, you have the principal quantum number, 1, 2, 3, all the way to 7. And then across to the right, you see the possible subshells that can be developed from that quantum number. If n equals 1, 1s is it. If n equals 2, then you can have a 2s, but you can also have a 2p. If n equals 3, then you can have an sp and a d. If n equals 4, then you can have an sp, d, and f, because 4 is 0, 1, 2, and 3. n minus 1. 4 minus 1 is 3. Okay? So that's how we lay them out first. Then the diagonal arrows tell you how these orbitals are filled based upon the Aufbau principle, from lowest energy to highest energy. What we find is that 1s is no problem. 2s is no problem. 2p to 3s, no problem. 3p skips 3d and goes to 4s and fills that one before we go to d's. Then you go back up to the d, because now it turns out that the 4s is lower energy than the 3d because of all the electrons and their penetration effects that are combining to make a d orbital, 3d orbital, higher energy than the 4s orbital. So far, so good. That's why these diagonals, they keep you honest with the energy levels. So we're going from 3p to 4s rather than over to 3d. Then you can go back to 3d, 4p to 5s, and then 3d, which is a higher energy than 4p or 5s. Right? That's how you fill them based upon lowest energy to highest energy. Well, if we go to the periodic table and look at how that's filled, right? The first period is 1s, 1s1, 1s2. Right, based on that. Then we go to the second period, lithium, beryllium is 2s, 1 and 2. Then we jump across here to aluminum, that's 2p. 2p, 1, 2, 3, 4, 5, and 6. Okay? Then we go over to period 4, and based upon that one, we go down to 4s rather than 3d. We go to 4s first. Then when we get to scandium, we back up to 3d. Right? So the fourth period has 4s, then 3ds, then back to 4ps. Okay? Then we go to 5s and 4d. and then 5p. Okay, we're following those diagonals. Did I say 5p? Yeah, 5p. Then we go to 6s, cesium. And then we go to 5p, but then we have a break. And we go to 4f. And once we get the 4f done, then we go back to 5d again. 5d's go across here, then 6p's. Then we go to 7s's. And then we go back up to 5f with actinium. And then when we get when we get finished with 5f's, we go back to 6d's till we get here. And then the rest of the way is 7p's. And that finishes the periodic table. That's as high as we go. That's as many as we know. Right? 118 protons. Okay? We'll practice some. Let's see. I'm going to have to erase some of this to make room. All right. So for example, write the electronic configuration for sulfur. First thing you need to know is how many electrons. So you go to your periodic table, find sulfur. It has 16 protons. And since we're not working with ions yet, then we have 16 electrons. Right. Let's put them in. Let's fill out the orbitals in order of energy first, and then put electrons into them. So 1s first, then 2s, then 2p, then 3s, then 3d. Right. Let's see. Wait a minute. Let's skip. That's p. 3p, then 4s. That's probably enough. We may not need that many, but that's the energy order. 1s2, 2s2, 2p, 3s, 3p, and 4s. And we keep going if we want. Right, so we count them off. Maximum of 2, maximum of 2, maximum of 6, and 2. So 2, 4, 10, 12. So we got 4 more to go, and they'll go right there. And that's as far as we need to go. That's the electronic configuration of neutral sulfur. And if we look at the periodic table, we find that we've done the 1s's, we've done the 2s's, 2p's, 3s's, and 3p's up to 4th position from the left. 1, 2, 3, 4. 3p, 4. If you know how the periodic table is structured, you can do this without memorizing the order, as long as you know where to find it in the periodic table. So this would be the valence electrons. 6 valence electrons. Who else has 6 valence electrons? Oxygen and selenium. They have similar chemical behaviors. Not exactly the same, similar. Okay? How about barium? That's a biggie. Barium, way down over there in the 6th period. 56. Okay? So, if I follow along with the periodic table, I know I'm going to need 1s, 2s, 2p, 3s, 3p, 4s. Right? Then I go to 3d. Right? Then I jump back to 4p. I get that 4p across. Then I go 5s. Then I go 4d. Then I go back to 5p. And then I'm down to 6s. I know that's as far as I need to go. Why? Because barium is at the beginning of the 6th period with the s orbitals. So I don't need any more. Okay? Then we know that S's can hold 2, P's can hold 6. 6, 2, 6, 2. D's can hold how many? Count the number of elements. 10. They can hold 10. Then we'll hold 6, 2, 10 again, and then P's 6. And then barium is in the second column from the left, 2 more. So let's count them up and see if I got all 56 in there. All right, 2, 4, 6 is 10. Then 2, 6, and 2 is another 10. And then another 10. And then 6 and 2 is 8. And then another 10. And then 6 and 2 is 8. All right, so it's 10, 20, 30, 40. 40 and 16 is 56. So all of the electrons are counted for. Okay. That's the full. Yep. That's the full, a complete electronic structure for these elements. We have a shorthand way of expressing them also. Is if we consider the noble gases, do they look like any of the noble gases? Well, if we take this one, right, we discount the valence shell and we say, which one looks like 1s2, 2s2, 2p6? That's neon with 2, 4, 10. So if we substitute that for here and just put the valence on the outside, that's a shorthand way of writing it. Okay? If we do it for barium, what's the highest energy level here? Which one would look like, if we go to barium, back up 1 to cesium, and then up to the next period, xenon. Xenon then has 54, and what's left over? What's left over is 6s2. That's the shorthand for barium. It preserves the valence electrons in their special orbitals, but it says all of these are core. Okay, that's the shorthand version. Europium, I'm not going to have you do that one. It's just in here for giggles. Right. So if you write it in its shortened version, where's europium? Let's see, 4f7. So it's right over here. Count it. 1, 2, 3, 4, 5, 6. Well, we have to count lanthanum. 1, 2, 3, 4, 5, 6, 7. Right. So how would you do that one? Well, you back up through lanthanum to xenon, right, xenon, and then you follow it along. You got to have a 6s2, there it is, and then a 4f7. And that covers europium in a shorthand version, instead of having to write all the structure out. All right, now we're going to look at periodic trends. What else can we glean from the table? Useful information. Once the table was established, then scientists started looking at various characteristics of these elements and said, is there a trend the way we've got the table constructed? We're going to look at these 3 different possibilities: ionization energy, electron affinity, and atomic radius. Ionization energy has a definite expression that's required, that must be met in order to define ionization energy. And for that, we need whatever the element is in its gaseous state. Then we add energy to it. Right? We add energy. And what happens? We kick off 1 electron by adding energy. Right? This is the first ionization energy because it removes 1 electron from the neutral atom. That's the first ionization energy. You can have more than 1. Right? We could go to this one like that. And then the second ionization energy would be a 2 plus charge plus an electron. Okay. And you can keep going for however many electrons are available. What you'll notice is that it only happens one electron at a time, because this energy is different from this energy. In fact, this energy is going to be the lowest. This one's going to be higher than that energy, always. And it's logical, right? You're trying to move another electron from a positively charged ion. It's going to resist. So it takes more energy to get this second electron away. Now, for some, well, for all elements, once you've removed the valence electrons and you start getting into the core, then the amount of energy required jumps way up. It can be 6, 7, 8, 10 times as much energy required to remove. In this case, the first ionization energy that's for magnesium from its core electrons is 10 times as much as for the first one. And if we look at the electronic structure of magnesium, which is 12, right? 1s2, 2s2, 2p6, 3s2, right? And 12, right? The first two are coming from the valence shell, right? So it's just simple electrostatics. But when you try to remove an electron from the core, then you jump way up. So the first two electrons are predictable and sequential, but the third one is going to be a monster. So this is the definition of ionization energy. How much energy do you have to put in to get that to happen? So this energy, we're putting energy into the system, which means this value will be positive. Ionization energies are always positive. Now, how about the trends? The periodic trend for ionization energy can be described first in terms of periods. Right? As you cross the period, the amount of, from left to right, the amount of first ionization energy increases, because you're at essentially the same energy level, but you're adding more protons. You're increasing the nuclear charge, which is more strongly holding the electrons. You're adding more protons. So the trend from left to right for ionization energy, right? Left to right, ionization energy, this is the first ionization energy, increases. Should be true for the second also, but we're going to keep it simple. And it's due to the increasing nuclear charge. How about if you go, let's see, is that on that same? That's left to right. If you go up or down in the groups, if we go down in the groups, right, the ionization energy decreases. Okay, so it takes less energy to remove the first electron here than it does up here. Reason for that is core electrons. When you think of a nucleus and you have various electrons out here, but you have them here too, and you got all these positive charges here, multiple positive charges, these inner electrons are shielding the outer electrons from that nuclear charge. Plus, these electrons are further from the nucleus. They're already at a higher energy state, so it takes less energy to get them loose. Okay. So if we reverse that trend, right, if we go up, that's an increase. So overall, the trend in the periodic table is first ionization energy increases from lower left to upper right. Okay. Let me see. What point are we trying to make here? What you'll notice is that within a period, right, we've identified the noble gases in red, right? So in each one of the periods, we're going from left to right, atomic numbers increasing, left to right. We see a general trend, right, from lithium through beryllium, boron, carbon, nitrogen, oxygen, up to neon. The trend is an increasing first ionization energy, right, in any one of these periods. Okay, but we do get some anomalies. Notice that when we get to beryllium, boron jumps down. Nitrogen to oxygen, it jumps down a little before it goes back up. We have to explain that also. Why is it not linear? Well, the major factor is electron repulsions. If we look at, let's take one simple one, say nitrogen to oxygen. Okay, let's look at nitrogen structure versus oxygen structure. So this is 7, this is 8. We already did this one. 1s2, 2s2, 2p4. And nitrogen is 1s2, 2s2, 2p3, right? Okay. So these guys only have one orbital in each, right? So they've got electrons in them like that, like that, like that, like that. So they're the same type. They're same gathered together. They're going to have similar repulsive effects. But when we get to these, we got 3 of them orbitals in that subshell. 3 here are going to be like that, like that, like that. But oxygen is going to be like this, 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 like that. Right? These guys are separated from each other in different orbitals. This one has to pair up. These 2 electrons are going to push against each other harder than the others. So that means this electron is more likely to be kicked off, take lower energy. Right? So when we go from nitrogen to oxygen, the energy for the first ionization dips down a little bit due to that repulsion. Okay. Let's see. Electron repulsion. We see a similar effect from beryllium to boron, but I'm not going to go into those. Not enough time. So let's see if we understand what's going on here. Which atom would require more energy to remove an electron? Sodium and chlorine. Well, there's sodium in the 3rd period. Chlorine's over here on the right. So the period from left to right is increasing. So more energy would be required for the chlorine, wouldn't it? Yep. How about lithium and cesium? Lithium and cesium are in the same group. So as you go from lithium down to cesium, you're decreasing the amount of energy. So more energy is required for the lithium than for the cesium. First ionization energy. How about the second ionization energy for lithium or beryllium? Right? Lithium has 3, so it's a 1s1, 1s2, 2s1, and beryllium, I think it's 4. Yeah, 4. Beryllium has 1s2, 2s2. Okay. We're talking about the second ionization energy. The first ionization energy would be like this, give you a positive charge. The second ionization energy would try to remove a core electron. Whereas beryllium would be down to 1, and now that one would remove 1 electron from this valence shell. it would be lesser energy required. So lithium's second ionization energy should go jump way up compared to beryllium, because we're trying to take out a core electron. And this graph it came out of your textbook. It just shows the difference, right? If you go from sodium, magnesium, aluminum, and we're working through as you increase one proton each, sodium, magnesium, aluminum, all the way through to argon. And we find that the core electrons for sodium would be the second ionization energy. The core for magnesium is third, so forth. Aluminum down to, let's see, what's that? Sulfur. Down to sulfur, you got to go for the seventh ionization energy to get into the core. Okay, that was ionization energy. The next concept is electron affinity. Now, the tendency is to assume that electron affinity is just the inverse of ionization energy, but it's not. You're starting from the same place, and I didn't make this point before, so I'm going to make it now. Why does that element have to be a gas? I'm saying it does. It has to be a gas. We're gauging the amount of energy required to move an electron, right? If it's a liquid or a solid, some of that energy is going to be used to melt it or vaporize it. We don't want that, because that has nothing to do with the electron. So in order to gauge the energy, this has to be a gas. And then, instead of the electron being kicked off, the electron is attracted to it, right? And that produces a negative charge. So how do we measure the energy there? The energy here is measured as a negative value, because if that electron drops from a higher energy level into into any one of the energy levels around that atom, it's going to give up energy. Energy is leaving the system, so it has to be negative. So the more negative this number, the stronger the attraction for of the electron for that atom. Okay? All right. So when they say more negative, think stronger attraction. In general, as we go across a period from left to right, the electron affinities become more negative. Right? So what that means is the attraction is much, much stronger as you go from left to right. And it becomes more positive as you go down the group for similar reasons as the ionization energy, because of the shielding effect. So the trend for electron affinity is from lower left to upper right, more negative, which means stronger attraction. All right, atomic radius. This one's a little more difficult to get a handle on. We mentioned it, or I mentioned it a little earlier. How do you know what the extent of the atom is, right? Because you've got these electrons out here and you don't know where they are, right? Not really. You know probabilistically where they are. So the atomic radius is what we call operationally defined. It depends on the method you use. Right? If you have two atoms, the same atoms, bound to one another, like the diatomic elements, like H2 or N2, O2, F2, Cl2, I2, then you try to measure the size of that molecule, right? The size of the molecule and the distance between its nuclei, and then you just cut that in half. And that'll be the atomic radius. That's called the covalent radius. Well, okay, my slide talks about metallic radius first. Okay. Actually, metallic radius is not that difficult to determine because metals, when they solidify, they tend to arrange themselves in regular patterns. Right. So this metal might have, right, elements stacked to one another. Right. And in the second semester, we'll talk about those different patterns, but for now, this is good enough. And when you fire X-rays at them, right, some of them bounce off the surface, some of them go down and bounce off this surface, and so forth. And when they come off, they're out of phase. So what you do is you look for the angle from the vertical. You look for the angle, which gives you the highest energy output. That means they've constructively interfered with one another. And then you use what's called the Bragg equation to tell you what's the distance between the layers. And once you know the distance between the layers, the distance between the nuclei, just take half of it, and that's the atomic radius. So that's the metallic radius using X-ray diffraction. The covalent radius uses various different techniques to determine what's the distance between nuclei in diatomic elements, homonuclear diatomics. It could vary from X-rays to firing electrons at them, even neutrons, and microwaves even. Right? It just depends on the method. It's operationally defined. I posed a question to one of my PhD advisors one time. I was using a chemical technique to extract manganese from the soil. I says, okay, I know that this manganese comes off easier than the next fraction, right? So how do I explain that to my committee? You know, what's happening here? He says, oh, it's easy. It's operationally defined. I said, okay, as long as you're on the committee and you can back me up, it just, you know, all I'm saying is that as I increase the strength of the extractant, then I'm assuming that the bond that's holding that manganese to the soil particles is stronger for the successive extractants. That's all I can say about it. And then we try to make some inference as to which manganese is more available. Well, the one that's easiest to extract, of course, would be more available to the plant. And then might want to speculate. I can say something about, well, how do we get the others to be released so that the plant doesn't suffer from deficiency? Okay. So what do we say about the atomic radius as a trend in the periodic table? Well, as we go across the period from left to right, the atomic radius tends to decrease. And for similar reasons to the ionization energy, we're increasing the strength of the nuclear charge. Right? We're adding more protons, but we're not increasing the size of the shell. Right? The strength of attraction is shrinking the electron cloud because the number of protons is being added. And even though we have more electrons out there, still we're in the same period or energy level, so it tends to shrink as we add more protons. So the size of the atom from left to right decreases. When you go up and down in a group, then you are going from this energy level to the next energy level. We're increasing. Remember, N, it references energy and size. So you're increasing the size. So it's logical as you go down with the increasing principal quantum number, you're increasing the size of your electron cloud out. So it gets smaller as you go from bottom to top. So the overall period is lower left to upper right, decreasing atomic radius. And this is a general trend. It works pretty well for the representative elements, the first two and the last six. Once you get into the transitions, they can be like this. So we kind of have to ignore them. That's why this table only shows the representative elements. First two columns, last six columns. And you can see across a period, the decrease, and down in a group, the increase in size. Okay, which should be the larger atom? Oh, I'm out of time, right? 2 o'clock. Oh, way past out of time. How much more do I have to do? Not too far. Okay. We can knock these out pretty quick. Sodium and chlorine, are they in the same period? Yes. So chlorine should be the smaller, sodium should be the larger. Now, when you make an ion, that's a different story. Sodium is a metal. It likes to release electrons, likes to give up electrons. When it gives up an electron from its third period, now it's into the second period radius. So it could very easily be smaller than chlorine once you lose that electron. How about larger here? Well, the larger one's going to be cesium. It's in the same period, in the same column, but it's way down the list. Which is larger, the hydrogen 1s orbital or the lithium 1s orbital? Think about the nuclear charge. Hydrogen only has 1 proton. Lithium has 3 protons. So its 1s orbital is going to be drawn even more strongly toward the nucleus. So the larger one is going to be the hydrogen, which is lower in energy. The closer you are to the nucleus, the lower the energy, based upon the fact that we have to put energy in to get that electron to move out. So lower energy is closer to the nucleus. Now, the reason it's lower energy is because it's got more protons pulling on it. Right? Arrange these according to increasing ionization energy. Oxygen, fluorine, and sulfur. Well, let's see. Oxygen would be like here, fluorine would be here, and sulfur would be there. Relative positions in the table, right? These in the same period, this one's in the next period, but the same column. So the trend is lower left to upper right, ionization energy. So ionization energy should increase, increasing ionization energy. So it should be sulfur, oxygen, fluorine, right? Okay, atomic size. Increasing atomic size should be just the opposite. Come on. There we go. Based on the trends that we discussed. Okay, final thoughts. It's the number and type of valence electrons that primarily determine the chemistry of atoms. And at the first level, it makes sense because ask yourself, what does an atom see first when it approaches another atom? It's electrons, right? So they're responsible for the chemistry. Now, they're only there because of the nucleus, but the nucleus doesn't participate in the reaction. It only influences the behavior of the electrons. Electronic configurations, they can be determined by the way the table is organized, right? We've shown that. Certain groups in the periodic table have special names. All right, we can cover those. Divisions of the elements in the periodic table into metals and nonmetals. Right? Oh, that's it. Okay. Sometimes I surprise myself.